I saw a video from Live Overflow showing this cool hiring problem from Nintendo, where you essentially have to reverse some output to an input. When the video went up, some commenters noticed that linear algebra was involved, which really captured my attention, so I decided to tackle the problem. Man, was it a cool problem. And I think it is a great place to introduce some basic math concepts. We will build the cracking program from scratch with nothing more than Python. We will also not shy away from the math behind the solution, but don't worry. Math is often viewed as an arcane, nebulous art that is difficult. You may have this position, and it is my goal in this video to hopefully challenge that view. Math is a beautiful field, and is a tool for us to reason about complex systems, such as the one we are about to see. The beautiful part of this problem is that it highlights the intersection of computer science and math. Let's get started. In this video, I will introduce to you functions, preimages and inverse functions, Cartesian products, modular arithmetic, and matrices. These all may sound scary, but in time, you will see they are very approachable concepts. Let's first split up the forward function into 3 visually identifiable stages. The first stage essentially takes a list of bits called C and substitute each value in C. This new list is now called D. Formally, we will call C and D vectors for reasons that will be more apparent later. We will also call the operation stage 1 performs on C sigma 1. Sigma 1 is what we in the math world call a function. A function is in essence a mapping from inputs to outputs. Think back to your early schooling. You may have seen f of x equals x squared, which means take a number x and perform a computation on it, namely square it. This f function is like a machine that consumes an x and spits out a new value. Continuing this analogy, we are abstracting away the complexity of stage 1 into this new guy, sigma 1, which is like a machine that performs some computation on C. This is what mathematicians do all the time, take complex ideas and give them names so that we can more easily talk about them. As for why I decided to call stage 1 sigma 1, mathematicians typically use Greek letters, which are faster to write. The words stage and sigma both start with S, making it easy to remember. Additionally, sigma will stand out and cue to us that we are dealing with math and not code. Continuing on, the second stage performs the scrambling operation, which we will call sigma 2. Finally, the last stage, which we will call sigma 3, substitutes each value in C and compresses 2 consecutive elements into 1 element in D. Graphically, we can think of the input data transforming as it goes through each stage, and when put together, we get a kind of data transformation pipeline. How do we reverse this pipeline whereby we can reconstruct the input given some output at the end of the pipe? Maybe it will help to think about a smaller situation. Consider 2 operations A and B. We will denote operation B, then A, as AB, and denote the reverse operation as this kind of AB to the negative 1 power. But this is read as AB inverse. As for why we write A and B in the opposite order, this will be explained later. But first, to understand the inverse, we need to understand what an identity operation is, which we will call I. The idea is quite simple. The identity operation is the operation that does nothing to the input. In other words, it maps the input to itself. So consider the function f of x equals x. This is the identity operation as running the f machine on any input gives back the original input. Notice how this function notation, we write the input being operated on the right side. This explains the opposite order for A and B, as when we perform the operation AB on some input x, we will write it as ABX, which looks like we are first executing B on x, then executing A on BX. Now, given some operation A, we say that A inverse is the operation that brings you back to the original input after applying A, and vice versa. So in other words, A inverse A is the identity operation, which is also A inverse. So imagine rotating an image 90 degrees clockwise. The inverse operation is rotating the image 90 degrees counterclockwise, as performing both operations in either order will be as if you did nothing, also known as the identity operation. Back to our original question, what is AB inverse? It turns out that AB inverse is B inverse A inverse. Intuitively, this makes sense. Consider putting on your socks causes operation B. Then putting on your shoes causes A. The combination of putting on your socks then your shoes is AB. The inverse operation is thus taking off your shoes, A inverse, then taking off your socks, B inverse, which is none other than B inverse A inverse. All this formalism was to establish a key idea used throughout this entire video. The reverse of a sequence of steps is the inverse of each step done in reverse order. So looking at our pipeline from before, we can think of the entire data transformation as this, where we perform sigma 1, then sigma 2, do this 256 times, and then sigma 3. Using the inside above, the inverse of the entire process is thus this, where we perform the inverse of sigma 3, then the inverse of sigma 2, then the inverse of sigma 1, and then we do a bunch of repetitions. Okay, so now we have a place to start. We just need to figure out the inverse of sigma 1, sigma 2, and sigma 3. And from there, we can reverse the entire process. Let's figure out sigma 3 inverse, as remember, the first operation performed is on the far right of the expression. In the picture, this is what stage 3 does. It looks at two consecutive values in C, substitutes them for some values, and then these are XORed together. How do we reverse this process? Rather than reversing the entire vector D, how about we reverse each entry in D to two consecutive values in C? This is actually a lot easier. So given some value di, we can just brute force all possible pairs of C values and see which turn into di. This is not so bad, as C is an array of 8-bit integers, meaning we only need to test 256 squared values, which can be quickly done on a computer, and we will now program that now. Okay, so what we're trying to do here is we're trying to find two pairs of characters who will substitute and transform into a particular D value. So let's call this function find XOR match, and this takes a D value that we are trying to recover. So what we want to do is return a list of these pairs, right? Because we're going to brute force the answer in the end, and we're going to brute force through all of the possible first characters, going from 0 to 256, as characters are 8 bits, and we're also going to brute force the second character with the same idea. We're going to let C1 and C2 range from 0 to 256. Now, we're going to check if the substitution of C1 XORed with the substitution of C2, right, give us our D value. And if so, we add that to our result like this. So notice that we are using a list and not a tuple. There is a good reason for this. This will make our life easier in the future, but in the end, we're basically brute forcing all pairs of C1 and C2 and seeing which one gives us our D value. So now that we've done that, all we have to do now is return our result, and that's it. Okay, so we have now just reversed each entry in D, right? And from there, we can derive some vector that, when passed through stage 3, or sigma 3, will output D. It turns out that the values of D we care about are here, which can be found by converting the string into a byte array. Reversing each di gives us a list of pairs that transform into di. Call this list Ci. A portion of each Ci is now shown. Now notice that selecting any element from Ci and mushing them together into one long vector will be a vector that turns into D after passing through stage 3. This idea of picking one element from an ordered list of sets and mushing them together into one list has a name. This is known as the Cartesian product. So let's explain what a Cartesian product is. Let A and B be sets, which you can think of as collection of elements. We say A cross B is the Cartesian product of A, B, representing the set of all pairs A, B, where little a is in big A and little b is in big B. So for example, consider 1, 2, 3 cross with AB, and you end up getting this set. Geometrically, you can think of the Cartesian product as grid points, like this. Do you see how reversing stage 3 involves a Cartesian product? Rather than taking the Cartesian product of 2 sets, we are taking the Cartesian product of 16 sets. Unfortunately, I can't draw a 16-dimensional space, but anyways, explaining the Cartesian product is useful because it turns out that Python has a nice function in itertools that allows us to iterate through a Cartesian product. We will use this to brute force the final answer, which is why knowing names and terminology comes in handy. You could easily look up how to do something when you know its proper name. In any event, given a vector D, we can compute all vector C, whose transformation under sigma 3 or stage 3 is D. We write this idea in math notation like this. So flatten is just a function that we make that takes our Cartesian product and smush it into one long vector, as technically the elements in Ci are pairs and the Cartesian product results in a list of pairs as opposed to one contiguous vector, which we want. In code, this is how we would implement it.
Okay, so what we are now trying to do is reverse stage 3 or find a pre-image of stage 3. So what I'm going to do here is I'm going to import from itertools product, which will help us iterate through a Cartesian product, which is exactly what we need. So let's make target equal list, and it's going to be array.array, and we're going to be converting this string into a byte array. Okay, and I forgot to mention you also got to import array to convert the string into a byte array. But because this string is 15 characters long and not 16, we're going to just append a 0 to it, because remember, we want our C vector to be 32 bits long, and well, in order for that to work out, your target has to be 16 bits long. So what we will now do is we're going to use this previous function that we created before, where we could find a pre-image of each character in D, which we call target. So I'm going to call this individual pre-images, and this is also going to be a list. And so what we do is we're going to perform a map. We're going to map each of our values in target using the find XOR match function. And so this will take every single character in target and then find its pre-image using find XOR match, and then it will put it into a list. Okay? So then what we do is now we just got to iterate through the Cartesian product. So I'm going to say for each Cartesian product in, so product using this function from itertools, product of individual pre-images. But it turns out that we need to actually unpack it, because product doesn't take a list. It takes a list of arguments, and in order to supply a list of arguments from a list, we need to use this unpacked operator. And so then we now have a pre-image, like a pre-image of stage 3. So let's call this stage 3 pre-image, and we will flatten the Cartesian product, right? Where flatten, like we said, was the function that takes a Cartesian product and converts it into one contiguous array. But now we have to implement this flatten, which is not that hard. All we have to do is say define a flatten function. We take a Cartesian product, and of course it's going to be in list or an array and or a list, and we just go through each pair in our Cartesian product, because remember our Cartesian product is a list of pairs, and we need to basically like unpair those and turn it into one long list. And this is why we made them a list, because we can use this extend function to basically concatenate these pairs into our res right here, and then we can just return res. And so this basically lays the groundwork for how we're going to iterate through all pre-images of stage 3, and then in the end we're going to find the answer we're going to find the input that turns into this hire me byte array.
I will now introduce some new terminology. This equation shown previously is known as, quote, the pre-image or inverse image of D under sigma 3. In essence, the pre-image of an output value is the set of all input values, whose transformation gives you your output value. Because this idea of a pre-image is so close to the idea of an inverse operation, we will use the same notation. Therefore, with this new idea, we can reformulate our original problem as finding the pre-image of this vector under this map. This terminology will be useful as we move on to reversing stage 2 and stage 1. The key insight to reversing stage 2 is that we are basically solving a system of equations. You may have seen a linear system of equations in school looking kind of like this. We can succinctly write this equation as a system of equations in matrix form, like this. Notice how we go from the matrix representation to the original system of equations. We do this kind of strange left-right, up-down multiplication, and this strange multiplication will come in handy later. But the basic idea of solving these systems is that we would choose a variable we want to solve for, then eliminate other occurrences of this variable in other equations. The name of the variable chosen in one equation is called the pivot. We will box all pivots. Let's work an example. So let's pick x in the first equation and eliminate the other occurrences. We can do this by multiplying the first equation by -2, then adding it with equation 3, giving us this new system. In matrix form, it looks like this. Notice what we did. We multiplied the first equation by -2, which is a totally legitimate operation. So suppose x equals 10, then obviously 2x equals 20, which occurred by multiplying by 2 on both sides. The special choice of -2 allowed us to cancel out the x term in equation 3 when they were added together. Adding two equations together is also legitimate. Consider if x equals 10 and y equals 5. Then obviously x plus y equals 10 plus 5, which is 15. The same logic applies. We can also clearly see the elimination process occurring in the matrix form, where there are zeros in the first column under the pivot. We can now continue this elimination trick by selecting y in the second equation. We can cancel the y in the first equation by adding both equation 1 and equation 2. We can then eliminate y in equation 3 by multiplying equation 2 by -2, then adding both equations, giving us this new system. We can then clean up the system by dividing each equation by their pivot, which once again is totally legitimate, and we get this new equation, this new system right here. And in matrix form, it looks like this. But notice how in the elimination process, we get a bunch of zeros above our pivot. We can now eliminate z, giving us this final solution. And in matrix form, it looks like this. Do you see how in the final matrix, there is a bunch of 1s down the diagonal and zeros everywhere else? Once we have manipulated our matrix into this form, we are done, and we can solve the system of equations. This special matrix is called the identity matrix, because when you perform the strange multiplication with this matrix, you get your original input. Therefore, the essence of the elimination method is to get to the identity matrix through a series of row operations. Okay, so now that we have a feel for how elimination works, we will use this technique to solve a way bigger system, but with a twist, whereby we use a different kind of addition called XOR. Let's take a look at the XOR operation. There are a few ways of interpreting the XOR operation, which we will denote with this circle plus symbol. Typically, X XOR Y, where X and Y are either 0 or 1, is described as 0 if both X and Y are the same, and 1 if they are different, which is shown in this table. Another interpretation, though, is using modular arithmetic, whereby XORing two numbers is known as, quote, addition modulo 2. The idea is that when you add two numbers, you think of a clock, where once you reach past 1, you wrap back to 0, similar to a clock wrapping back to 1 after 12. What's nicer about the second interpretation is that we can easily see that all our nice properties of regular addition holds with XOR, namely we have associativity and commutativity. We also notice that 0 acts like a regular 0, where any number plus 0 is the original number. 0 is also known as the additive identity element because of this property. With our identity element, we can now define an inverse element. Notice with XOR, the inverse element of any element is the element itself. Any number XORed with itself gives back the identity element 0. You can verify this using the table or the clock diagram. We can ground these terms in our regular addition, where the additive inverse is simply the negative of our number. So for example, the additive inverse of 5 is negative 5, because if you do 5 plus negative 5, you get 0, which is the identity. And also if you do negative 5 plus 5, you get back identity. So we can now extend our XOR operation to dealing with vectors as opposed to bits, where you just perform the XOR operation on each entry in the vector. So here you can see that we have a vector of bits, which in the future you'll see that we're actually going to be XORing two 32-bit integers. Well, you just XOR each bit and then you get a new 32-bit integer or a new bit vector. Okay, so all of this exposition all leads to why elimination works. We are taking our pivot and we're multiplying it by a value, turning it into the additive inverse of the term we are eliminating, so that when we add the two equations, the term we want eliminated disappears. Looking closely at stage 2, we see a very familiar picture by unwrapping all of the for loops. It looks like a system of equations we saw, but using XOR as opposed to regular addition. Okay, so we can substitute all of these strange looking terms here by actually computing them, and this is what a snapshot of our system looks like. So we can then convert the system into matrix notation like this, and we will now write the code to generate this matrix.
Okay, so now we have to generate our matrix. And I'm just going to use NumPy here because it makes our lives a little bit easier when we start doing some matrix operations. I mean, you could do this without NumPy, but it's common enough that I think it's helpful. So what we're going to do is we're going to define a function called generate matrix. And this matrix initially starts out as a matrix of zeros. And this matrix will be 32 by 32 because it turns out that we have 32 equations with 32 unknowns. Now, we also have to specify that the d-type of this matrix is an int, because the entries in our matrix are integers and they are not floats, which NumPy defaults to, and it's going to act wonky if we try to do XORs. So what we're going to do now is we're going to generate the matrix. So the idea of our matrix is that the row and the column will be specially crafted so that when we do a matrix multiplication, we basically get our system of equations. And so we're going to say for j in range 0 to 32 and for k in range 0 to 32. So you should notice that we're pretty much matching the variables used in the hireme.cpp file. And we're just going to say our matrix at row j and matrix at column k will equal to the value of our diffusion. So the jth integer in our diffusion, bit shifted k times to the right, and then we just extract the bit at the rightmost position. And so this should correctly populate our matrix, and we'll just return this matrix now.
Okay, so the format of this matrix is such that every entry at row I in column j is this value, right? And we'll just call this matrix A. So reformulating our matrix notation, we get this, AD equals C, where D and C are vectors. And to solve D, given some C, we basically need to perform elimination similar to what we did before. However, doing elimination every time is extremely inefficient, and it turns out that we can pack all of the elimination steps into a single matrix that, when multiplied, will replay all of our elimination steps. So it turns out from linear algebra that if you perform your row operations on both A and the identity matrix I simultaneously, I will turn into a new matrix, and this matrix turns out to be A inverse. Once we calculate A inverse, we can now solve the equation AD equals C. What we do is we multiply both sides by A inverse, we get the identity on the left side, which gives us D, and then finally we solve for D, which is A inverse C. Okay, so while this is not a full proof, the idea that you can get A inverse by reflecting the row operations onto the identity matrix can be seen by thinking of our row operations as EI. So performing our row operations, we get this right here, where we take AD and we multiply it by E1, E2, all the way to like En, whatever that may be, and then we do the same thing to the right-hand side, C. Right, that's basically what we did, but we're using kind of like a matrix notation here. Well, the idea of elimination is that we eliminate the matrix A into an identity matrix, and so you end up getting ID, which equals D, and it equals to C with a bunch of elimination operations applied onto it. So from our definition of the inverse, it's totally plausible that this operation right here, E1, E2 up to En, is the inverse of A, as when you multiply it with A, you get identity. We just need to replay these elimination actions onto the identity matrix so that we get the matrix representation of this E1 all the way to En. But the actual proof for why this works is much more technical, and this is more of a high-level overview of why this is the case. Okay, so elimination using XOR surprisingly is easier than elimination using regular addition. We can eliminate a row by checking if it has a 1 below our pivot and simply performing bitwise XOR on both rows. Remember that the additive inverse of a bit is itself. Let's look at an example. So here's our matrix from before. The box number will be our pivot, and we will eliminate down. Notice that row 6 has a 1, which I put in bold, below our pivot. Adding row 1 and row 6, of course using XOR, will eliminate that value under our pivot in row 6, giving us this new matrix. So notice how we now have a 0 in place of that 1 from before. So we successfully performed the elimination step. Okay, so we just basically need to repeat this procedure for every pivot, giving us the final identity matrix, and we will now program the inversion operation in code.
So we will now do the matrix inversion at this point. So I didn't really talk about this before, but it turns out that we're going to need a function called swap, which takes a matrix, an I and a j, and it basically swaps row I and j. And the idea is that the reason why we might want to swap two rows of a matrix or swap two equations is that when we select a pivot later, we don't want our pivot to be 0. And because if it's 0, then we cannot perform an elimination. So we would want to look for another row that doesn't have a 0 in the pivot position and swap it, and then we can continue with the elimination. And so this is a pretty standard swap. What we're going to do is we're going to create a buffer variable, and we're going to copy the ith row of the matrix. And the reason why we do this is there's some weird technicalities about like array references in Python, and so if you attempted to write the swap without doing the copy, you're going to get unexpected results. And so I'm going to just do it this way, where we just copy the rows and then perform the swap using our copies. Okay, so this is a pretty standard swapping operation where we just buffer the ith row, and then we swap out the ith row with the jth row, and then we fill in the jth row with our buffer. So now the thing that we did talk about is how to perform elimination with XOR. And so I'm just going to call this add, right? And basically what this says is that we're going to take the jth row and bitwise XOR it with the ith row, and then change the jth row. So in code that looks like this, we're going to take the jth row of the matrix, bitwise XOR it with the ith row of the matrix. Okay, that's about it, right? So now that we have these two basic row operations, we can now perform the inversion by doing a series of row operations on our matrix, and then hopefully get the identity. And in the process, we reflect those row operations on the identity. So we're going to define a function called invert, and it takes a matrix. So what we're going to do is we're going to make a matrix called res, which is going to start out as the identity matrix called mp.I, and it's going to be 32 by 32 with dtype equal to int once again, because we don't want floats. And we're going to set current equal to np.copy matrix. So we're making a copy of our matrix so that we don't destroy our original matrix right here as we're performing row operations. Okay, so what we're going to do is we're going to basically loop through all of the pivots. So if we have a 32 by 32 matrix, we have 32 pivots, each one on the diagonal. So we're going to say for I in range 0 to 32, we need to now consider what is the pivot right now. So the pivot is on the diagonal, so it's going to be at the I, I position of the current matrix, whatever that is. And we're going to ask, hey, is the pivot equal 0? Because if it is, that's bad, and we don't want that to happen. So we're just going to scan all of the rows below us currently and check if that value is a 1, aka not a 0. And so if that's the case, then we can perform a swap with the ith and jth row right here, but then don't forget to also do it on your identity matrix so that we inevitably get our inversion. And then we break. So once again, we're letting j scan down the rows beneath our current row, which is row I, and we're asking, hey, does row j have a 1 in the pivot position? If so, swap I and j, and then stop scanning, and then we can bump back out here. So now that we have a proper pivot that's not a 0, right? If it were a 0, then we would have swapped in a proper row for there to be a 1. We can now eliminate down, so we're going to say for j in the range from I plus 1 to 32, so we're looking at all rows currently below us. If the value underneath our pivot is equal to 1, we can perform an elimination. If it's 0, it's already eliminated. We don't need to do anything. So we just add the current, we take our current matrix, and we add row I with row j. Remember, row I has our pivot on it, and so when we add it to row j, it's going to eliminate that entry. And we also need to do the same thing on our identity matrix. Okay, so now we just eliminate down. We also need to eliminate up, and so it's pretty much the exact same idea. So we're going to range from 0 to I, and if the current value above our pivot is equal to 1, we can perform an elimination. And so we're going to take our current matrix, eliminate on row I and j, so eliminate row j, and then do the same thing for our identity matrix. So once we've done that, all we got to do now is return res, because we've reflected all of our row operations on identity, and res is the result of doing that. And so once we return res, we get our inverted matrix.
Okay, so now that we have just written the code for writing the inverse matrix of A, right? And it turns out that the inverse is actually well-defined and it turns out to work. We just need a way to multiply a matrix with a vector, right? Because remember, in order to solve for D, we need to do A inverse C, and in order to calculate A inverse C, we need to multiply A inverse with a vector C. So we will now write the code for our strange multiplication.
We're basically done. We just have to figure out a way to multiply our inverted matrix with our vector C to recover our solution to our system of equations. And this isn't really that hard. If you know the formula for matrix multiplication in linear algebra, this should be pretty straightforward, but all we have to do is just kind of visualize the weird, strange, up, down, left, right multiplication maneuver that we do, and just translate that into code. So we're going to make a function called multiply, which takes a matrix and a vector. And inevitably we're going to pass our inverted matrix into this matrix parameter. So what we're going to do is we're going to say res, which will be our final product between our matrix and our vector, is going to start out as a list of zeros, 32 zeros that is. And now we basically need to compute each entry in this res vector. So what we're going to say is for I in range 0 to 32, we're going to have a value called sum entry, right? I can't really call it sum because that's a keyword, so I'm going to just call it sum entry, and that starts out as 0, which is appropriate because remember 0 is our additive identity. So whatever we do to 0, it's going to be reflected. So we're going to say for j in range 32. The reason why we do that is because we're now, in order to compute our entry, we need to move down our vector and then move left to right on our row in our matrix. So this j does that. It moves simultaneously across the row and down our vector of our matrix. And so our sum entry is now the XOR of, well, we XOR it with the matrix value at I, j. So once again, we're selecting a column I, and then we're scooting down the row using this j, and then we're multiplying it with the value in our vector. So this essentially moves down our vector and then multiplies it with the corresponding value in the matrix as we move across its row. And then all we do is we then set that as our entry in row in the ith position of our vector. Then we just return res. So anyone who studied linear algebra, this would look very familiar. The only difference is that we're using XOR right here instead of plus. But it's the exact same way. Just if you're not familiar with matrix multiplication, just think of the left, right, up, down move, and that's what we're doing right here. And then we just return res.
Okay, so we're basically done reversing stage 2, and we can now compute the preimage of C under sigma 2 to recover D. And formally, we would write it like this. The inverse of sigma 2 of C is A inverse times C. Okay, so now we just have to reverse stage 1 now, which will be a lot quicker now that we've established all the mathematical foundation. Stage 1, or sigma 1, simply performs a substitution for each value in C, and we will use a similar technique to the one done in stage 3. What we will do instead is build a lookup table. This lookup table will give us a list of characters whose substitution leads to the given value. So notice that each character is substituted for some 8-bit integer. That means that our lookup table needs to have 256 slots, one for each 8-bit integer. We can then populate our slots by iterating through all characters and inserting them into the corresponding slot, which we'll now do in code.
Okay, so in order to reverse stage 1 or find inverse of sigma 1, we need to build a lookup table. And this isn't that hard. We're going to make a function called build lookup table. It's not going to take anything. And so remember, our lookup table matches a value from our confusion array. So like these values here, and then give us a list of characters whose substitution gives us one of these values, right? And so that basically means that our lookup table has to have 256 elements because these are 8-bit integers and there are only 256 different ways, like 256 different 8-bit integers. So we're going to make 256 empty arrays or empty lists using this kind of list comprehension syntax. Okay, so now we're just going to iterate through all possible characters and watch how it gets substituted. So the idea is that we take a character C going from 0 to 256, run it through our substitution, and then we basically put that into our lookup table. So we're generating our lookup table by just brute forcing through all characters. So we're going to say take our lookup table and at the position where we're substituting our character C, and that gives us some index into our lookup table, and then we say, okay, at that index, C gives you that substituted value, and we're basically done. This is how you build up the lookup table, and then you can just return it.
So what we basically just did was we are computing the preimage of every integer under the substitution by tracking how the substitution maps each character. We could then compute the preimage of the entire vector under the substitution by using our Cartesian product as seen in stage 3. But do note that the preimage may in fact be empty, as it is entirely possible that there exists no vector whose substitution gives what we need. So notice how OXFA never appears in the confusion array, which means OXFA has no preimage under the substitution. Okay, so we've basically just laid the groundwork to build our program that cracks the input. So let's look back at the operations we need to execute. So here's the inverse of our entire data transformation pipeline. So it looks kind of like this. So we first need to take our output and compute its preimage under sigma 3. Okay, then we take that preimage and then we repeatedly compute its preimage under stage 1 and 2. And we do this 256 times, and I use this very suggestive notation right here, which looks kind of like multiplication. But we basically have to repeatedly compute the preimage of a vector under stage 1 and stage 2. Once we have done that, that should reverse our entire process, giving us our desired result. And we will now program that in code.
Okay, so we're done. We basically know how to compute the preimage of stage 1, stage 2, and stage 3. We just got to put all of our pieces together now to crack the final input that gives us this as the output. So let's set up our pieces now. So we're going to make a variable called stage 1 lookup, which builds our lookup table that we made previously, and then we're going to need a stage 2 inverse here, which is going to be the inversion of that matrix that we can generate like this. Because with these two pieces, we can find a preimage of stage 1 and stage 2. So in this for loop, we basically have a preimage of stage 3, and so we just need to pump that through the preimages of stage 1 and stage 2 256 different times. So we're going to set up a list of targets that give us this stage 3 preimage. And we're just going to pump it through the preimage 256 times using this for loop, and we're going just to reassign targets to the preimage of targets All right, and we're going to use a function that we will make later called compute stage 1 to pre-image, which will take our lookup table and our inverted matrix along with a list of targets to hit using into pre-image. Now, if we have successfully computed the pre-image of targets 256 times, we're basically done. We found a input that gives us this as the output. So we're checking that if our list of targets is greater than 0, just print out the first item in our target and then break, because we don't want to keep doing this for loop over and over and over again. So now let's implement this function right here. So we implement it like this. It takes up a lookup table and it takes an inverse and a list of targets. So given a list of targets, we need to compute a list of pre-images that maps into this list of targets, right? So our pre-images, when mapped under stage 1 and stage 2, will be in our targets. So this is going to be a list that will eventually return. So we need to compute the pre-image of each target. So we're going to for loop through each of the target and compute its stage 2 pre-image, which, if you recall, we multiply our inverse matrix with our target vector. Then with this stage 2 pre-image, we need to compute the stage 1 pre-image, which we'll write in like a Cartesian product form. So we'll write as stage 1 Cartesian product, because this isn't the final pre-image, but this is like the Cartesian product representation of it that will later transform into a pre-image. And so it turns out that this needs to be a list, and we're going to be using the map function, where we map every entry in the stage 2 pre-image. So map every character in the stage 2 pre-image vector and map it to the value to the list in the lookup table. So we take the character in the vector and then we map it to the list of characters in our lookup table. That gives us this substituted C value that's from this substitution. Okay, cool. But remember, stage 1 may not even, the stage 1 pre-image may not even exist, right? It might be empty. So we're going to make a Boolean called stage 1 has stage 1, has there a stage 1 pre-image like this, and it defaults to true. So now we just need to check if this is even a valid pre-image. So we do that by mapping through every character pre-image in the stage 1 Cartesian product. So remember, this is a list of lists basically, and each list is a pre-image for a character in this stage 2 pre-image. And so we just want to check that the length of the pre-image list for each character is non-empty. Because if it's empty, then, well, obviously stage 1 doesn't have a pre-image, and so we'll just set that Boolean to false and then break out the loop. The reason we do this now is that now we just say, hey, does stage 1 have a pre-image? Because if it doesn't, just move on to the next target. There's no reason to continue looking at this target. But if it does have a stage 1 pre-image, then we basically unwrap the Cartesian product using the itertools function. So product, and we give it our stage 1 Cartesian product right here. And once again, product takes a list of parameters. It doesn't take a list. So we actually have to unpack this list using this unpacked operator. So now that we've got a pre-image from our Cartesian product, we just append that into our pre-images like so. And the reason why we use a list is because product actually gives a tuple, and we want to turn into a list. It doesn't really matter actually, but I'll just do it like this. So we now compute it. Now we can now reverse the stage 1 and stage 2 pre-image, and basically we are done. And so this is the completed program here, where we take our target, we compute the stage 3 pre-image of it, and then we take that stage 3 pre-image and then we pump it through the pre-image of stage 1 and stage 2 256 times, and if our list of targets is not empty, then we found a match and print it out, and then we can break.
Okay, so if you actually run this code, it turns out to take a really long time because of how inefficiently this code was written and how slow Python is. So rewriting this program in a faster language will likely yield a much more performant program, which was the case when I rewrote it in Rust. However, the goal of this video is not to solve the problem the fastest, but to move through the thought process for how you could solve this problem and to showcase some cool math. Hopefully you enjoyed this video and learned some math along the way. Our code will be posted to GitHub along with a transcript of what was said in this video.